Section 8.3, problem number 2. A little hard to read, but that's the best I can do to get it all on the page. The U.S. Department of Transportation, NHTS administration, reported that 77% of all fatally injured automobile drivers were intoxicated. All right, so that's the report, 77%. Now, a random sample of 52 records showed 35 were intoxicated. All right, so we got 35 out of 52. All right, so I'm going to write some numbers down here. N is 52, and X, well, X or R, the number of successes is 35. Okay, so right away, I know what P hat is, all right? P hat is going to be 35, and I know I'm dealing with proportion because they give us so many out of so many. Obviously a proportion then. 35 out of 52, and that comes out to 0.673. Okay, so then what is Q hat? We might as well get it while we're here. Q hat is 1 minus P hat, so this is going to be 1 minus 0.673. I got 0.327. Now, we're not asked for that directly, but I think we're going to need it. Okay, so first of all, what is the level of significance? 0.10. All right, so we're going to run this thing at 0.10. We're going to run a hypothesis test at 0.10. Now, the problem does go on to say, do these data indicate that the population proportion of driver fatalities related to alcohol is less than 77% in Kit Carson County? All right, so evidently, we went to Kit Carson County, we looked at 52 records, and we found that 35 of them involved intoxicated drivers. And we want to test now what did we get? We got, what, 67%. The national average is 77%. So we want to know, is it, they tell us, less than. And there is some evidence for it, but let's see if it's significantly different, right? There is a numerical difference between 67% and 77%. But is it statistically significant? Or can we attribute the difference just to variation in our sample? All right, so what is the null and alternate hypotheses? Well, we're testing that it's less than. So do you see one that's less than? How about this one here? That's it, right? This is the only one that's less than. So the null states that it's equal to 0.77. The alternate that it's less than 0.77. So we'll go with this one here. Now, B, what sampling distribution will you use? All right, well, this is a proportion, so we don't use student's T. So it's either going to be, we're going to use it or we're not going to use it, right? We're going to use it if NP and NQ are greater than 5, and we're going to, the normal sense, okay, less than. Well, those aren't the conditions. Now, it's not this one, it's not these. It's got to be this one. Now, you just know it's got to work, or they wouldn't be giving us the rest of the problem. So, but can you verify it? Can we verify that N times P is greater than 5 and N times Q is greater than 5? Well, N was 52. Yeah, 52. And P, we computed P to be that, well, okay, I'll do it this way. 35 over 52, because 52's cancel, I get 35, which is greater than 5. And then in Q, I'll have to do it this way. 52, now Q is this value right here, 0.327. Now, just look at it. This is 30% of 50. Well, 30% of 50 is bigger than 5. Okay, you don't actually need the number. Is it bigger than 5 or is it smaller than 5? It's bigger than 5. Okay. So, yes, NP and NQ are both greater than 5, so we'll select this one. Yeah, we're going to use the standard normal, which means we're using the Z-curve. Now, what is the value of the sample test statistic? This is going to be Z star, and we're going to get it using the calculator, right? There's a conversion formula for it, but we can get it on the calculator. So let's go to our calculator and type all this in and do run a one proportion Z test. So on your calculator, press the stat key over to the test key. And ... we're going to scroll down to item number 5, which says 1 prop z-test. Prop, proportion. We're going to do 1 proportion z-test. Here's the information that we're being asked for. First of all, what is P0? Well, that's what we're testing. We're testing that it's 0.77, right? I mean, P0, if you come back here, P0, that's really H0. H0 says that P is 0.77. So we're testing that we're at 0.77. N was 30, or X, that's 35. That's the number of items we observe with a particular characteristic, being intoxicated in this case. N was 52, that's our sample size. And we are running a less than test. So run your cursor right down here to the less than, press enter to fix it, and then go to calculate, press enter. So here's what comes back, right? We're running a less than 0.77 test, and the z-value I got was negative 1.67 if I round it off, but the p-value is 0.0484, say if I round it off. So let's finish some of these off here. Part C. Find the p, oh, well, okay, this part up here. What's the z-star value? We're not going to use it, but it's negative 1.67. If we were using the traditional method, using the table in the back of the book, that's what we would use. The p-value, there's our p-value right here, 0.0484. Now, what would be a proper sketch? We're using a left-tail test. Yeah, left-tail test. All right, so what have we got? This is a two-tail test. Rule that one out. This is a right-tail test. Rule that one out. That's a right-tail test. Rule that one out. This is the only left-tail test. Now look at that value right there. What's our z-star value? Our z-star value is negative 1.67. That looks like it's between 1 and 2. All right, this looks like it. It's a left-tail test. The number looks right, so I'm going to choose this one. Now we've got a p-value here, so that's what we're going to use to decide to reject or fail to reject. So here's p and alpha. Now p is 0.0484, and for some reason they have us using an alpha of 0.10. Okay, so we'll do it. It's a textbook. Anything can happen. So 4%, right, this is almost 5%. 4.8% is less than 10%. So for less than, remember what to do here? If it's less than, you reject H0. Now, just a quick reminder. When I see a less than, I think of small, and I'm dealing with probability, so it's a small probability. So I'm looking at my observed value and comparing it to the claimed value, right? The observed value was, what was that, 0.67. The claimed value is 0.77. I'm saying there's a small probability that I'm going to see that, yet I am seeing it. So this is unlikely. If a small probability, it's unlikely. So I would be seeing something that's unlikely if that hypothesis was really true. So I'm either going to believe I'm seeing something unlikely or that the hypothesis is not true. So I don't think I see things that are unlikely. So I'm going to reject the hypothesis. Okay, that's how I get to reject. So what are we going to do here? At alpha equals 0.10, we reject the null hypothesis and conclude that the data are statistically significant. That's the one we want. If you reject, you're saying that there is a significant difference between your observed value and the claimed value. Now I'm going to write it here. Here's what we observe. Here's the claim. We're observing, I think it was 0.67, and the claim was 0.77. Clearly there's a numerical difference. Is it statistically significant? We are saying yes. The 6.7 is far enough away from the 7.7 to claim that the difference is real. It's not just due to random variation in our sample. So we're going to go with this one right here. And then part E asks us to make an interpretation. So what are we doing? We're rejecting the H0, right? We're rejecting 77%. So what are we going to say? There is sufficient evidence at 10% to conclude that the true proportion of driver fatalities is less than. That's what we're doing, right? There is sufficient evidence. This says there's insufficient. There is sufficient evidence. So we'll go with this one right here. And problem's done.